Our next speaker, my last, but you have two to go, and good lucky for you, is Angela Belcher, nanotechnologist. She's professor of materials science and engineering and biological engineering at MIT. In 2001, she co-founded Senzyme, a Cambridge startup. Angela Belcher works in a highly interdisciplinary field called biological self-assembly. Michael Crichton and Bill Joy may have scared your pants off about this. We'll see what Angela has to say about it. It finds ways to get viruses to produce industrial materials, including pieces of integrated circuits, microscopic biosensors, and liquid crystal structures for computer screens. Her company, Senzyme, intends to use biological self-assembly to make electronic materials and biotech-specific applications. According to a short profile in Popular Science, my Bible of science, where Angela was named one of Pop-Size Brilliant 10, I love that Popular Science way, Belcher's viruses can produce stronger, smaller, potentially more complex materials than those produced in high-tech engineering facilities. And the process doesn't pollute or harm animals. A must for Belcher, they write, a vegetarian whose dogs eat only homemade organic foods. Angela Belcher says that most of the grad student applications that she gets are not from biologists. And when I look at someone's application, she says, I don't care where they come from, but instead I ask, are you willing to start from scratch and learn an entirely new approach? It's getting harder and harder for me to choose because more and more people want to learn from scratch. It's been wonderful. I'm sorry I'm missing this one, but I'm sure it'll be great. Please welcome Angela Belcher.
Well, I really appreciate the invitation to be part of this really spectacular meeting, and these last talks today were just wonderful. I'm going to tell you a little bit about what we're thinking about in my group at MIT right now, which is, can we convince organisms to make materials they normally wouldn't make? And I'll tell you some of the reasons that we're thinking about that. I did my PhD work on how abalone grows shells, actually right off the coast of Santa Barbara. There's marine organisms, abalone, gastropods, that make an incredible material. This is basically made out of calcium carbonate. It's about 98% by composition calcium carbonate, basically chalk, but about 2% by composition biological molecules, mostly proteins. But it's actually 3,000 times tougher than its geological counterpart. It's also made in ocean temperatures, using totally non-toxic materials, and it produces no toxic waste, and very little waste at all. I remember when I was in graduate school, I had worked on isolating the mechanism for how abalones grow shells, and it's based on nanoscience, which I'll tell you a little bit about in a minute. But I remember standing on my desk looking at the periodic table one day and thinking that, what other kinds of materials could you convince an abalone to work on? And I went through the periodic table and I outlined other kinds of materials that I thought I could convince an abalone to make as well. But I quickly ran out of it. And I started thinking, what about semiconductors? What about electronic materials? Organisms haven't had the opportunity through evolution to make these materials. Can we force them to do it in the lab on the order of a couple of weeks? So I'm going to tell you a little bit about that. So this is an abalone shell, which is a self-organizing structure. It's coded at the genetic level. It's self-correcting, it's self-healing, and it'll make a copy of itself the same way every time. And I'm going to pass it around so you guys can look at it. You can try to kind of break it, and also think about the fact that chalk you can easily snap with your hands. Chalk is based on micron-sized technology. Shells and pearls are based on nanotechnology, so that's half the secret. So this comes from the National Nanoscience Initiative in terms of a publication that was put out in terms of what nanoscience is. And people call me a nanotechnologist, and I get called a nanotechnologist all the time, although I've never called myself that. I think of myself as a material scientist that likes to work on very small things. But so it's basically, how do you take a couple of atoms and arrange atoms in a way that they have really interesting properties? And these interesting properties are scale. They're small. It's making more compact materials, more compact devices. But one of the things that's most interesting about nanoscience is when you look at atoms as just a couple of collections of atoms working together at a time, their optical and electronic properties change. And so they're different than that of bulk materials. In addition, when you take materials and you make them on a really, really small scale, they also change physical properties in that they become very strong and very tough. And the abalone shell that I'm passing around is an example of an extremely tough material that's based on building with nanoscience. So what is nanoscience and what is nanotechnology? Nano comes from the prefix, which means it means 1 billionth, so it's all about size. It's size that when we define what nanoscience is, but it's not really the size that is the overwhelmingly exciting property. It's what the electronic properties are, what the optical properties are, how things change as a function of size. And nano comes from the Greek word that means dwarf. And so it's really a technology that deals with things on the billionth of a meter scale from about 1 to 100 nanometers. And so this happens to be the natural size of where biological molecules are. And so that's why it's so exciting to me. So this is the last list I'm going to give you, and then I'm going to show you some pictures of how we're using, basically exploiting viruses and bacteria and yeast to make materials for us. There's a lot of applications in terms of nanoscience. There's computing technology, making things smaller, making things faster. There's new kinds of information processing. There's medicine, which you've heard some about in terms of smart prosthetics and medical implants and tissue engineering and platforms for growing organs. There's the environment. There's a couple different environmental aspects to it. There's the environmental aspect of, can you make things without waste? Can you make things without having an excess of toxic materials around? But then there's also the environmental aspect of it is, can you make new kinds of batteries? Can you make more efficient solar cells? And then there's Department of Defense applications in terms of looking for hazardous agents, making super strong, super lightweight cars, which are also have environmental impact as well. And so I was asked to give a talk at the National Nanoscience Initiative maybe 6 months ago, where I was supposed to talk about what the most challenging aspects of material science are. And to me, this was a dream come true. And this is a small part of the list that I talked to these different government agencies and said, this is a list of what I'd like a material to be able to do. I'd like a material that could actually self-assemble. And I'd like a material that could actually self-correct if there's a mistake. I'd like a material that could heal itself. So if you're building a circuit and it breaks, it's out in the field, it could actually just repair itself. I'd like it to have a material that can actually be made at room temperature and room pressure, so not at very high pressure or hundreds of degrees Celsius. And I'd actually like a material that generates little waste. I'd also like something that could span from multiple length scales, from nano to macro, and interface with biology. But what my dream really is to have a material that's completely genetically addressable, where you could have a DNA sequence that codes for the synthesis and assembly of an electronic material, and it could correct itself as it went along. I'd also like to have a material that's responsive to external cues, and this is a project that we're working on called the electronic stem cell, where you have a cell that could be any kind of material you want it to be. You just feed it one kind of nutrient, and it grows a semiconductor. You feed it a different kind of nutrient, and it grows a magnetic material. So it's genetic and active control over materials processing. And then, of course, I'd like to have a material that's inexpensive and scalable. And to have a general platform to be able to make medical diagnostic materials, medical implants, self-assembling electronics, optical materials, basically everything that's based on a genetic code. And you might look at this and say, well, when I wrote my first grant proposal, I had two reviews. One, this is incredible, and the second one, she is insane, and that was about almost 6 years ago, and I now have a lab that supports about 25 people. But So there's two different aspects to it. There's the fact that cells like eukaryotic cells, like yeast or human cells, already have this amazing ability to process information. They can assemble, they can correct, they can build proteins, they can signal within a cell, they can signal externally within a cell, and there's also bacteria cells that can also do the same thing. But the hard part is now can you convince these organisms to now work on something that they haven't had the evolutionary pressure to work on? And this is the concept of self-assembly. So I'm, for the most part, a self-assembling system. No one had to design exactly where all the pieces of my bones went, where my vesicles go. Basically, I was assembled from almost scratch. But in addition that I can repair myself, and for the most part I'm self-correcting. But a lot of people try to understand what the idea of self-assembly is, and this is a snowflake. And a snowflake is a wonderful example of self-assembly because a snowflake in the center has some kind of piece of dust or dirt that acts as a nucleus that allows this beautiful and exquisite structure just to assemble itself. So we'd like to have the same thing, have an electronic component or optical component just assemble itself based on some small piece of information that's at the center. And so we think the way to do it, of course, is biologically. And you might ask why biologically. My answer is because this is the way that's already formed in living systems. And this is a scale bar here that represents 100 nanometers across. And this would be part of a circuit that would be in your chip. And so this gives you size. Now, sitting on it, superimposed, are sizes of biological molecules like proteins or DNA or a ribosome, the machinery that actually makes your proteins. You can see how much smaller they are than these components of this electronic chip. So our idea is, why don't you start with something that's already small, something that already has a genetic link, and ask it to make materials for you. And so one of the ideas is to take a ribosome, which is this natural machinery that actually reads a messenger RNA sequence that codes for the production of every protein in your body, and ask it not to grow proteins, but instead to grow semiconductors, and instead to grow magnetic materials. So can you have a sequence that says, okay, put this particular nanoparticle here and attach it to a different kind of nanoparticle? So here's some examples of some natural materials that already occur. One is this coccolithophora. This is a unicellular algae made out of calcium carbonate. Another is the abalone shell that's going around in the audience right now. This, if you fracture it and you look at it in high-resolution microscopy, what you notice is that it actually comes from stacks of crystals that stack on top of each other to make this brick wall-like structure. And this brick wall-like structure is what makes it such a strong, tough structure. Now, these individual crystals that make it up are actually on the nanoscale. Another example is a diatom that's made out of SiO2, made out of glass, basically, that self-assembles and makes a beautiful, exquisite structure that is also has nanoscale features. And another example is a magnetotactic bacteria that's a bacteria that has small magnets that are used in navigation. Now, all of these are made in ocean temperatures using non-toxic materials, and all of these structures are coded at the DNA level. This is an example of several different diatoms. These are tens of microns across, more like the width of human hair. And this is, again, in high-resolution microscopy. But they come in these exquisite, beautiful shapes. And what's so interesting to me about this is that they all actually grow in the same environment in the ocean. And they all have the same chemicals to start with. They all have the same temperature, but they look so different from each other. So this says that the shape and order of these materials are actually coded at the DNA level or the genetic level. This, again, is just pictures of what the abalone shell that looks like that's going around in the audience is. It's a very uniform structure. And the reason that it actually has the structure is that it has a template that's actually a protein that's not that different than skin or hair, which tells exactly every atom where to go and how to line up. So what we're interested in doing is creating the same kind of template that doesn't work for a material like calcium carbonate, like your bones or shells, but works for materials that make up electronic devices. And if you look at the periodic table, which was my inspiration for getting into this field, is that nature uses only a couple different elements, calcium and barium and silicon and phosphorus, but has left all the other elements unmade for biological control. And so what we've been doing is forcing the organisms to work with these elements to make interesting materials that we want them to work with. And so the idea is to have a really specific interaction. You have proteins in your body that are antibodies that are really specific, that bind to small organic molecules. We want to combine the same idea of really specific interaction with the idea of self-assembling electronics to make new materials, which we call evolved hybrid materials. And so you might ask the question that it's taken an abalone millions of years to be able to have control over this material. And graduate students at MIT are about 4 to 5 years. So how are you going to get that same control over a material in the length of less than a graduate student? And the answer is that we decided to take it an easy way. We decided to look at how scientists are already developing interactions with proteins and drugs. And it's a process where we use a virus that has single-stranded DNA. And we clone into the DNA, and we convince the virus to have a random protein on one end of the virus that we can use to manipulate to get it to force it to work with materials. I'm going to show you a little bit of a complicated diagram, but then show you a movie that's based on this. So what we do is we take 1 billion different viruses that are all genetically identical to each other, but they differ based on a small protein insert on one end of the virus. And then we force it to interact with a semiconductor wafer. Most of them don't bind. This is kind of a Darwinian process. Most of them don't bind, and you throw them away. Any that have an affinity for this material, we remove. Viruses can't replicate themselves, and so we infect them into a host, which is a bacteria. We make 1 million copies. We purify them. And then we say, OK, now can you stick to this material under different environmental conditions? Most won't be able to bind, and we throw them away. And we keep going around putting pressure on them to be specific for this kind of material. Then we just actually pop out their DNA and sequence it and know something about the material interaction. And so here's our movie that my students made, where you take 1 billion viruses and force them to interact with a semiconductor. So here it goes. We force them to interact. Most of them don't have any affinity for them. They get washed right away. Some are nonspecific. You compete them off the surface through evolution or selection pressures. Then you have a couple of viruses that are now chemically specific for this material. You take these viruses now and you infect them into a bacterial host. The bacteria now is a factory that will clone this for you and make millions and millions of copies. And so it goes into the bacteria, it takes the bacteria machinery and exploits it and copies itself, and then pours them all back into solution. And now you have billions of viruses to use to try to grow a material. And so our idea was, instead, you've heard about something on the head of a pen. Our idea was, can you grow electronic materials on the head of a virus? And here's, can you grow nanometer-sized materials on the head of a virus? And this is a cartoon of what it would look like. Again, this is high-resolution microscopy, with this is about 1 micron scale bar. And this is a collection of electronic materials that we grew on the head of a virus. This is about 1 million times magnified, where these are 5 nanoparticles that are electronic materials that are grown on the head of the virus. And if you can see these alternating stripe patterns, these stripes actually are individual rows of atoms that are making up this material. Well, then we said, well, it's interesting to see if you can make these materials. Let's see if we can make wires so we can make transistors to be able to hook up components. And so what we did was we took sequences and we cloned them back into the virus and convinced the viruses now to make wires. And so these are virus-based semiconductor wires that they're actually pretty perfect. They're all grown basically in solution on the coat of a virus. Then basically we're working on engineering them to be specific to wire up electronics, where they'd be able to go exactly where you want them to go. You'd be able to grow the material, and if you break it, it would be able to actually self-correct or self-heal. And so these are some of the, this is real data. This is individual viruses that were convinced to bind to an electrode on a device, and then actually grow an electronic connection between the two sides. Here's another movie which has to do with our idea of how to use viruses to make display technology in solar cells. And so in this idea, we throw in viruses in high concentration and convince them to grow electronic materials just on their heads. which they do. But what we found is that actually, just like the snowflake, they actually naturally align themselves into perfect crystalline structures. And so we're exploiting the ability to grow a material and the ability to self-assemble it, and they have liquid crystalline properties which are completely tunable and exploitable, and you can actually make a film of this. This is a 99% virus film that you can pick up with forceps or tweezers, and the virus, as we've coded, exactly how far apart the electronics we want to be are. Again, looking at nature, we've decided to think about how spiders spin silk, which is they take a high concentration of a protein solution and they push it through a small hole called a spinneret. And we've done the same thing, but we've electrospun, or we've spun viruses to form continuous fibers, where these viruses can actually incorporate into them our electronic and optical materials to make fibers that we're using for textiles. And the last thing that I wanted to just mention was the idea of actually having yeast that are the same kind of yeast that you use to make beer or to make bread. And I've challenged my students to make beer and nanoparticles at the same time, where we're using these yeast as factories to create particles in solution. And this is what our factories look like. These are yeast that we're culturing, where all these the yeast, each one is responsible for making about 200,000 particles, semiconductor particles. And this is actually a yeast that is connected to a semiconductor. It's a light micrograph, so it's about 5 microns across. And it should be scalable because it's scalable in the beverage industry. So with that, I'd like to stop by saying I think that these organisms give a possibility for making environmentally friendly, self-organizing, self-correcting structures. And this work is only about a little over 5 years old, and we've really started to be able to start getting the kinds of properties that we'd like these organisms to make in about the last year. And I thank you for your attention.